Hey there, space enthusiasts! Ever wondered what goes down when galaxies have a cosmic collision party? Well, you're in for a treat, because today, we're diving headfirst into this intergalactic spectacle. But before we blast off into space, do us a solid. Hit that subscribe button and give us a thumbs up so you never miss a cosmic beat. So, what's the deal with galaxies crashing into each other? Get the right gear and you'll hear the universe humming wherever you turn your eyes in the sky. Now, it's important to note that sound cannot propagate through the vacuum of space. Instead, we're referring to the subtle vibrations of gravitational waves. You might already be acquainted with a similar phenomenon discovered many decades ago, known as the cosmic microwave background. It's essentially the residual glow from the colossal explosion that marked the inception of our universe, commonly referred to as the Big Bang. This pervasive microwave radiance was a groundbreaking discovery in its own right, effectively cementing the Big Bang as the predominant theory of how our universe came into existence. Nevertheless, it had a significant drawback. Despite being the earliest light we can detect from our universe, it was emitted almost 400,000 years following the Big Bang. To probe even further into the past, we require a backdrop not composed of light, but rather comprised of the ripples within the fabric of space-time. In 2023, scientists collaborating within NANOGrav have proposed that they may have detected precisely this through a clever technique. By employing exotic celestial bodies as an expansive gravitational wave detector, they have managed to measure the faint resonance of space-time itself. This gravitational wave hum could potentially be the echo of the universe's very birth. In a prior episode, we discussed the LIGO detector and its utilization of lasers to meticulously gauge minuscule alterations in the length of a tunnel brought about by the passage of gravitational waves. These gravitational waves stretch and compress space-time, thereby altering the duration required for light to traverse from one end of the tunnel to the other. However, detectors like LIGO are solely attuned to a specific class of gravitational waves. Similar to light waves and sound waves, gravitational waves can manifest in diverse frequencies. LIGO can only monitor a segment of this spectrum, the high frequencies. This encompasses cases where binary systems spiral rapidly toward each other, executing hundreds of revolutions per second, culminating in a tremendous collision. Nevertheless, this limitation also signifies that LIGO cannot detect the much earlier phases of these binary systems when the objects are orbiting each other at a considerably greater distance. As these orbit significantly slower, the gravitational waves they generate exhibit lower frequencies and energy. In contrast to a colossal collision, they give off a subtle hum that amalgamates into a unified signal. Larger black holes make more substantial contributions to this signal, with the most pronounced contributors involving pairs of supermassive black holes commonly found at the cores of galaxies. These binaries, featuring black holes billions of times the mass of our Sun, are expected to be rare occurrences because they should only form under exceptional circumstances, such as the merger of two galaxies. In the process of galaxy mergers, due to the vast expanses of empty interstellar space within them, they predominantly pass through each other. Actual collisions of stars or planets are a rarity, yet the gravitational attraction among stars causes them to congregate into a single collective galaxy, and the supermassive black holes within these galaxies form binary systems that continue to orbit each other long after the apparent completion of the galaxy merger. These remnants of galaxy mergers are what we would predominantly detect in the ultra-low frequency range, approximately in the nanohertz range. However, akin to how the human ear cannot perceive ultra-low frequency sounds, LIGO remains deaf to this cosmic symphony. If we could attune our instruments to this phenomenon, we might gain fresh insights into the processes surrounding galaxy mergers and black holes. But that's not all. One of the most riveting aspects of the gravitational wave background is its potential to provide a window into the earliest moments of our universe's existence. Let's swiftly recap our knowledge of the cosmic microwave background. This microwave radiation represents the earliest light we can observe because, during the initial 400,000 years, the universe was impervious to light. What does it mean for the universe to be impervious? Initially, the universe was excessively hot for neutral matter to form. Electrons and protons could not combine to create neutral atoms due to their elevated energy levels. This state of matter is referred to as plasma, the same substance that constitutes stars, and the universe was filled with it. The light was trapped within the plasma, incapable of traversing space without colliding with charged electrons and protons, continuously absorbed and then emitted. However, as the universe expanded and cooled to a point where protons and electrons could congeal into neutral hydrogen and helium atoms, it became transparent. The light was at last liberated. This light was subsequently stretched by the universe's expansion until it transitioned into microwave radiation, which is why the cosmic microwave background serves as the earliest observable light of our universe. However, gravitational waves do not consist of light. They are manifestations of the very fabric of spacetime itself. Plasma does not obstruct them. To gravitational waves, the universe has been transparent almost since the moment of the Big Bang itself. They can permeate this plasma barrier and offer us a glimpse of the universe's very inception. These primordial gravitational waves, having traversed vast cosmic distances, have been significantly redshifted due to the expansion of spacetime. Consequently, they now manifest as ultra-low-frequency gravitational waves, much like those emanating from black hole binaries. Collectively, these diverse sources give rise to what is termed a stochastic gravitational wave background that spans a range of low frequencies. How can astronomers extract this invaluable information regarding black holes, the Big Bang, and more? Can we construct an improved LIGO to perceive how the Earth responds to these immense gravitational waves? LIGO operates by transmitting two light beams along orthogonal tunnel arms. These beams are reflected by mirrors situated at the terminus of each tunnel, and upon their return to the starting point, they are compared with each other. This setup enables us to gauge the extent of space-time distortion in one direction by utilizing information from the other direction. Regrettably, if we were to devise a new iteration of LIGO to detect these gravitational waves, we'd require tunnel arms of significantly greater proportions than anything currently achievable on Earth. The reason for this lies in the inverse relationship between frequency and wavelength of a wave. Ultra-low frequency waves possess extraordinarily extended wavelengths, necessitating observation across far greater distances to discern the impacts of these gravitational waves. For nanohertz waves, signifying one complete oscillation occurring over a billion, or 10 to the power of 9 seconds, a rapid calculation, which is wavelength equals wave speed divided by frequency, informs us that the wavelength would extend to approximately 10 to the power of 17 meters. To provide a sense of scale, the distance between the Earth and the Sun, known as an astronomical unit, spans 10 to the power of 11 meters, while a light year encompasses around 10 to the power of 16 meters. The wavelengths we are dealing with are on the order of tens of light years. It is unfeasible to construct equipment suitable for this endeavor on Earth or even within the confines of our solar system. Our ambitions must extend beyond our immediate celestial neighborhood. However, instead of awaiting humanity's expansion beyond the bounds of our solar system to become a spacefaring civilization, the astronomers at NANOGrav have employed a clever stratagem. You may recollect our recent discussion regarding pulsars and how we explored the exceptional stability of these incredibly dense neutron stars. Pulsars emit beams of light from their poles, and we can perceive the periodic signals produced as these extensive beams sweep around and intersect with the Earth, repeatedly and with remarkable regularity. These precisely timed pulses function as cosmic timekeepers, capable of maintaining synchronization over vast cosmic distances. Consequently, we can harness the pre-existing pulsars to provide us with dependable signals originating from thousands of light years away. These pulsars act akin to the mirrors situated at the extremities of LIGO arms, But instead of reflecting a signal we transmit, they autonomously generate their own. NANOGrav has ingeniously devised a theoretical interferometer spanning thousands of light years, and all we require for its operation are the trusty radio telescopes we have employed for decades. Nonetheless, the accuracy of our calculations is contingent upon the quality of our observations. In the selection of pulsars for observation, it is imperative to ensure their suitability for the task. The most suitable candidates are meticulously chosen and assembled into a group known as the pulsar timing array. In the case of NANOGrav, they employed 68 pulsars selected based on their specific distinctive attributes. These pulsars had to be evenly dispersed across the celestial sphere to enable a comprehensive investigation into how substantial gravitational waves influence spacetime in all directions. Moreover, they had to be millisecond pulsars, signifying that they complete millions of revolutions every second. In our recent exploration of pulsars, we elucidated how these rapidly rotating pulsars are anticipated to be the most dependable and stable when it comes to the regularity of their pulses. Their precision rivals that of certain atomic clocks. These pulsars serve as the ideal temporal anchors distributed across both space and time. This consistency permits us to capture time measurements of the arrival of their pulses and to consistently record these measurements over several years, thereby enabling us to identify any evolving patterns. Naturally, the arrival times of these pulses can exhibit variations due to a multitude of factors. For instance, changes in the space between the Earth and the pulsar occur as both entities continue their movement through space. Nonetheless, these factors can be relatively straightforward to account for. Yet, some elements introduce less predictability, such as erratic fluctuations within the interstellar gas through which the light from pulsars traverses. These fluctuations lead to delays that are not attributable to the stretching of time and space. So, how can we separate the random noise in our data stemming from pulsars located thousands of light years away? The key lies in statistics, which enables us to distinguish the gravitational wave background from the random noise by considering the relationships between pairs of pulsars within the pulsar timing array. Much like LIGO, a solitary tunnel of observation is insufficient. We necessitate two pulsars stationed at each end of our conceptual tunnels. If similar fluctuations emerge from two distinct pulsars, it is improbable that random noise coincidentally aligns to create the appearance of synchronous behavior. It is far more plausible that there exists a common cause underlining these fluctuations, perhaps indicating that the photons emitted by the two pulsars are influenced by the same gravitational waves passing through them both. To analyze these correlations among pairs of pulsars, we consider their angular separation in the celestial sphere. If there is no gravitational wave background, we expect that there should be no correlation, and the graph should display a flat line at zero. Conversely, if the data conforms to a specific curve known as the Hellings and Downs curve, it suggests that the gravitational waves in the background are responsible for the observed variations. This is precisely what NANOGrav achieved. On June 28, 2023, based on over 15 years of continuous observations of their 68 pulsars, they reported robust evidence of the existence of the gravitational wave background. This graph is the breakthrough we have been eagerly awaiting. It serves as a hallmark of gravitational waves, which elongate in one direction and compress in the perpendicular direction. This aligns precisely with the patterns evident in this graph, where pulsars separated at right angles experience opposing effects as their photons journey towards Earth. Although the data's error bars may appear relatively wide, the researchers have computed that the evidence points to the gravitational wave background with significant statistical confidence at the 3 sigma level. In practical terms, this signifies a mere 1 in 1,000 probability that this outcome is a false alarm, a product of random chance. In the realm of physics, a 5 sigma result is regarded as the gold standard for discovery, but a 3 sigma level still provides substantial supporting evidence. As astronomers continue to amass and scrutinize additional data, they will be able to minimize these margins of error, ultimately substantiating an official discovery. So, What revelations lie hidden within this enigmatic gravitational wave background? While we are presently unable to disentangle the origins of this collective interference, we hold optimism that these methodologies will eventually grant us the ability to eavesdrop on particular supermassive black hole binaries, unraveling the cosmic insights concealed within their signals. In the interim, astronomers will persist in utilizing their colossal cosmic detector to compute our undulating journey amidst the tumultuous sea of space-time. Are you familiar with NANOGrav's work? What profound revelations do you believe gravitational waves might unveil? Share your thoughts with us in the comments section below, and see you next time on OVR Orbit Plus.